Hi everyone, this is Team RoboErectus, and this is our team presentation video for the 2024 CoSpace Rescue competition held in Qingdao, China. My name is 𝗔𝗏𝑚anian, and I'm here representing our team, myself, Darren, Qingdao, and Nicholas. Together, we participated in the RoboCup competition in Singapore in the Vision, Rescue, and ADL division. As part of our curriculum in school, we have worked on projects that require AI algorithms and programming, and this will be our first time competing in an overseas competition, the RCAP Qingdao 2024 for CoSpace Rescue. The core of our challenge is to compete against another robot, with the ultimate goal of accumulating as many points as possible. To achieve this, we developed a multi-objective optimization algorithm capable of handling various tasks in a prioritized manner. Some of the key priorities we set include finding the optimal path for navigation using efficient algorithms, maximizing points by strategically combining object collections, and locating and collecting super objects, which are crucial for high scores. We explored several pathfinding algorithms to determine which would be the most effective. Among these were Dijkstra's algorithm, greedy best first search, and the 𝗂𝑪𝑨𝑷 algorithm. Dijkstra's algorithm is reliable for finding the shortest path, but it tends to waste time exploring unnecessary nodes. Greedy best first search is faster, but often misses the optimal path. 𝗂𝑪𝑨𝑷 combines both of these approaches by considering the actual distance and the estimated distance, making it efficient for our needs. In essence, 𝗂𝑪𝑨𝑷 looks at the cost of the path traveled and the estimated cost of the goal, selecting the node with the lowest overall score. This allowed our robot to reliably find the shortest path to its goal without spending too much time searching. Navigation using 𝗂𝑪𝑨𝑷. 𝗂𝑪𝑨𝑷 is highly effective due to its integration of Dijkstra's algorithm and greedy best first search. The algorithm starts with initialization, setting up two lists, an open list for nodes that are yet to be evaluated and a closed list for those that have been examined. It employs a cost function to assess the actual cost and estimated cost to reach a node. This is crucial for its decision-making process. At each step, 𝗂𝑪𝑨𝑷 selects the node with the lowest total cost, calculated as 𝑓_cost, which is the sum of 𝑔_cost and ℎ_cost. By prioritizing nodes with lower f-scores, 𝗂𝑪𝑨𝑷 efficiently navigates the graph, focusing on paths that lead directly to the goal, while considering overall costs. This exploration process enables 𝗂𝑪𝑨𝑷 to find the most optimal route without missing potentially shorter alternatives. The algorithm continues iterating until it reaches the termination point, either finding the target node or concluding that no path exists. Bitmap creation. To create a map for our robot to use to navigate, we extracted BMP files from the game, source files, which depict the map image. Next, the obstacles and traps are marked as black on the map, and a black border is added around the edges of the map to prevent the robot from going out of the map. Different weights are assigned to represent the cost of various areas, allowing the 𝗂𝑪𝑨𝑷 algorithm to find the best route for traversing the map by considering the difference in speed when crossing certain areas. Effective bitmapping. To prevent our robot from getting stuck near walls or obstacles during turns, we increased the thickness of the black paint that covers the obstacles. This adjustment provides the robot with a more reliable path by accounting for its width when navigating near obstacles. Initially, the robot encountered difficulties when making tight turns, especially around sharp edges of obstacles, which caused its wheels to clip against walls or get caught in corners. We also created tree maps. The super map. We use this map for collecting super objects as they can spawn close or along the traps and obstacles. Traps and obstacles are extruded accurately here. With traps, a map used when there are objects in its inventory to avoid traps and obstacles. No traps, we use this map when the robot has no objects in its inventory and can travel through traps, but not obstacles. Object clustering strategy. We typically take 7 screenshots of the map and overlay them with some Python code to create a stacked image to see the general trend of spawns of the items and identify the common object spawn areas. To create clusters first, we mark the extreme x and y coordinates of each cluster to form square zones. These are then passed into our 𝗖𝑪𝑨𝑷 program, which translates the x and y values into a grid-based array for the algorithm to process. Inside each zone, the robot follows a random snake-like path to maximize coverage in the cluster and collect more objects. In this object point overview, you can see the points of each object. We can see that the Super and Super Plus gives the most points. This should be taken into consideration when planning the object collection strategy. Object combination. To create our point collection strategy, we created a graph showing the points comparison of each of the combinations. What you can see from the graph is that 6 blacks gives 240 points for a single run deposit. This is higher than 2 reds, 2 cyan, and 2 blacks, which we will call special, which only gives 180 points per deposit but generates a super plus object worth 360 points. However, going for special leads to higher average points. In 2 runs, 12 blacks gives a total of 480 points, while special gives a total of 540 points, which is 180 plus the super object of 360 points. This special results in a higher average score and is easier and faster to collect, as it only requires 7 objects for 2 full runs, compared to 12 objects for black. Next, our two-phase collection strategy. This optimizes our object collection strategy by saving time which is wasted only collecting one super plus at a time. For phase 1, the robot collects special combinations 4 times to generate 4 super plus objects, then collects all 4 objects on its 5th run. This switches our phase to phase 2. For phase 2, the robot collects special combination on its first run to generate 1 super plus object and collects a super object on the second run immediately, repeating this cycle until there's 1 minute left in the game. Due to the lack of time, it may not be able to collect the full super plus combination and instead collects RGB to generate super objects instead of super plus. This runs until there are only 10 seconds left, where it rushes to deposit any remaining items. Issues overcome. Initially, the robot could get stuck on squarish obstacles, so we modified the shape of obstacles from square to circular, reducing its corner-sticking tendency and plotting a smooth path around the circular curve. Secondly, repetitive object collection. To solve repetitive object collection, we made the robot move forward slightly and also added a variable to prevent collection until the robot began moving again. For the physical robot, initially it had a low deposit rate. We realized 2 corner markers were inadequate for frequent depositing and used the yellow trap zone as an additional marker, allowing for deposits from more locations. Here you can look at the bitmaps that we are going to use and the improvements we have made to it before we run the game for this map. So for our game, firstly, our robot goes to predefined zones and collects 2 red, 2 cyan, and 2 black to get the special combo. It repeats this 4 times until it generates 4 super plus objects. We do this so instead of 4 runs each only collecting 1 super plus object, we save time by collecting all supers at once in the 5th round. In phase 2, our robot only collects a special combination and a super plus object, one at a time, and repeats this cycle until the last minute. At the last minute, it switches strategy to only fulfilling RGB and goes straight to deposit since it has the RGB combo. Once it deposits, it spawns a super object which it collects subsequently. Finally, with this strategy, we are able to get 3170 points. For our results, we managed to make multiple improvements. The first being a dependable pathfinding algorithm which is reliable and time efficient. It navigates obstacles smoothly and rarely gets stuck, ensuring continuous operation with minimal interruptions. Secondly, it can consistently generate and collect super plus objects, optimizing its collection strategy for maximum efficiency and performance. Lastly, we improved the final scoring range to a final score between 2.9k and 3.4k, which is quite ideal. However, we still think we can further improve this algorithm. Now, how can this program be used in the real world? Drone-assisted search and rescue. In real-world search and rescue missions, drones can be equipped with advanced sensors like thermal cameras and lidar to scan and map disaster zones. These sensors detect humans and living beings by their heat signatures, allowing drones to locate individuals in need of rescue. 3D mapping for precision navigation. The data gathered from the sensors is processed into a 3D map of the area. GPS coordinates are integrated and transformed into a bitmap representation, providing a detailed layout for our pathfinding algorithm. Improved efficiency and effectiveness. Using this mapping and pathfinding approach, drones can efficiently navigate complex environments, avoiding obstacles and reaching critical areas faster. This improves the speed and accuracy of rescue efforts, potentially saving more lives in disaster scenarios. Next, we utilize ChatGPT extensively throughout our project, both for brainstorming innovative solutions to complex problems and for providing valuable assistance with programming tasks. It played a crucial role in refining our approach, offering suggestions for optimizing code and helping us troubleshoot challenges along the way. By leveraging AI, we were able to enhance our problem-solving capabilities and streamline the development process. In conclusion, our approach combined advanced algorithms with practical strategies to optimize our robot's performance in the RoboCup competition. We are proud of our results and excited about the potential improvements for future competitions. Thank you for the attention.